So this will be our last section for chapter 11, unit 11, and this is going to be called solubility equilibria. Essentially, it's how much will a solid dissolve in water. We know certain things dissolve really well in water, like table salt, for instance, and we know certain things don't dissolve really well in water. The calcium hydroxide that we were trying to dissolve yesterday, Sarah and Edith, doesn't dissolve very well at all. So that stuff would have a low solubility. And we can actually quantify that. Just like we have equilibrium constants for like weak acids and weak bases and other materials, we have equilibrium constants for solubility products. So we call that a KSP. The smaller the KSP, the less soluble this material is going to be in water at 25 degrees Celsius. The higher it is, then the more soluble it is at 25 degrees Celsius. So let's do a problem to figure out exactly how soluble something is. We're going to solve the following solubility problem to figure out the concentration of ions that are in a solution. That's usually what KSP problems are all about. Concentration of the stuff that's in the solution. Okay. And we do this just like an equilibrium problem. There's really no difference. These things should be very familiar. You think about the process in two parts. Part one, the AGI goes in a solution. That's part one. That's your initial state. Part two is the dissociation. So we break apart the AGI. This is nothing different than the H coming off the Cl for an acid-base problem. Since everything's a nice 1-to-1 ratio, there's no subscripts. We have x's on both sides, so our equilibrium is x. So I don't have written down the law of mass action, but that would just be this. KSP equals the concentration of the Ag plus times the concentration of the I negative. I do not include the AGI in the law of mass action because it's a solid and its concentration doesn't change. Okay. If there are subscripts, I'm just going to do if there's a subscript here, so like if it was AGI 2 and I had to put 2 in front of the I negative, I would have to raise that to the 2, to the second power. But that's not the case here, so we'll just keep it as is. All right, let's see. If I do this, I set up everything correctly. I've got 1.5 times 10 to the negative 16th, because that's my KSP for silver iodide. That equals x squared. So that means the solubility of silver iodide in moles per liter is 1.2 times 10 to the negative 8th. So you'll notice that the solubility in moles per liter is not always the same as the KSP. In fact, it's usually much different than that. The solubility product is the same always for silver iodide. It is always the same. It never changes. But the solubility in moles per liter can change. It can change if we were to add a common ion. So let's just say, for instance, we added in some sodium iodide. That is a huge arrow. Oh my goodness. So some sodium iodide comes into here. That's my common ion is obviously the iodide. That's going to force my equilibrium equation back in this direction. So that'll actually reduce the amount of iodide that I have. And obviously things change. This will be a little bit different. So my problem looks much different in this case. So we might see examples of that in some of the textbook problems. All right, let's take a look at a problem now that has actual coefficients. We've got lead chloride. We're going to dissolve this into some water, or at least try. Our initial concentration again is 0. We're going to change it now by x and 2x. We need the 2x because there's a 2 in front of the Cl. So you'll have twice as many moles of Cl as you will lead. So that's our equilibrium. We can find our law of mass action problem to look something like this. We can do the math here, divide by 4, take the cubed root of this problem, and the solubility of lead chloride in moles per liter is 1.6 times 10 to the negative 12th. If we want to think about this as an actual application, you could say, if I wanted to make a lead chloride solution, so I wanted to get lead chloride into solution, what is the most concentrated lead chloride solution that I can actually make before I start getting lead chloride to start binding back together into the solid form? And that highest concentration would be right here. So what is that? 0.016 molar, pretty low concentration. So if I had to make a 0.017 molar solution, or if I would try, I wouldn't be able to. It would 0.016 would be the saturated solution. Now there are things that I could do. I could change the temperature. The hotter the solution is, the higher the solubility is. So this number would go up if that number goes up. They're directly proportional. All right, so here's that common ion thing that I was talking about before. We got a salt again, silver iodide at 25 degrees Celsius, and it's KSP. We want to know its solubility in 0.05 molar sodium iodide. So now you have a solution of sodium iodide, and you want to put some silver iodide in with it, and you want to figure out how much silver iodide will be able to fit. Since the common ion here is the iodide, what's going to happen is we are going to force the equilibrium. My goodness, biggest arrow ever. We're going to force the equilibrium back this way because we're going to overload the right side with I negative. That's going to shift our equilibrium to the left. So our solubility should be less than in the first slide. Well, our initial concentrations are a little bit different now. We actually do have some I negative in solution. Our change looks like this. And so our equilibrium X for silver and 0.05 plus X for iodide. Now we can estimate that X is going to be very, very tiny. Why can we do that? Well, simply because KSP is really, really tiny. So that means that it's not going to dissociate very much and X is going to be small. So because of that, we can go ahead and do our approximation, our assumption that X is small enough, so 0.05 is fine for the equilibrium concentration of I negative. So if we do that, we do our calculations, we find out that X equals 3.0 times 10 to the negative 15th. And just to compare that to the first problem with silver iodide, the first solubility was 1.2 times 10 to the negative 8th. So this is actually, the solubility is much less, and that should make sense. All right. So that's solubility in a nutshell, and that's the last new piece of information that we have for this hugely long Unit 11. Just a note, indicators, I said I might talk about them a little bit. We really have everything we need for indicators. Indicators tell us the end point or the equivalence point. Hopefully those two things are the same of an acid-base titration. And the color change gives us that hint. So we won't talk anymore about indicators. All right, have a great weekend.